Hey there. So, in this video, we'll be talking about exponential models. So, what are exponential models? Well, they're graphs that are nonlinear and they have their curve, or more specifically, an exponential curve. So, how do you, well, it has this form right here, and it's different from the quadratic, because with the quadratic model, if you get the second difference, it's a constant value. Whereas for an exponential curve, if you get the second difference, you will notice it's not constant. However, what is constant is the growth and decay factor. Also, I should also mention that A in this formula is the initial value. So when x equals 0, and 0 basically turns B into 1, then all you're left is A. So when x is 0, will be the initial value. And the best way to see this is through some examples, which we will be going through in just in a moment. Um, you should also note that the growth and decay factors are equal and multiplied at regular intervals. So let's take a look at the first example. So we have this table here, and we have your D. D could represents distance or time or whatever you want it. And then you have here your P. And the growth factor is the secondary value minus divided by the initial value. So it's always so it's like this. So this is the secondary value, and this is the initial value. And then over here, the same thing. That's the secondary value, and over here is the secondary value, and it's always divided by the previous value. And you will get a constant number. In this case, it's 1.25 throughout this table, and that's the growth factor. That is essentially B here. So another way of telling if a graph is exponential, if you have this curve, and you notice with curves, it doesn't, it's sort of, let me just extend this line so you can see it, but you'll notice with these type of curves, they will always end up like that. It's like that, and it will go up like that. This will not, it will not go up. It will not go up, it will not turn into a parabola. Instead, it will just remain like that forever, like that. It will not curve up. Okay, and this one here, this is another example of how you can tell if it's an exponential model. You can tell right away by just the form itself. And x cannot equal, I believe x cannot equal 0. I should probably mention that there in the notes. I'll change that later. So you have something like this. Actually, x can be 0. But if you have an equation like this, then you can tell it is growth a growth factor. Okay, I believe that yeah. Let's look at the second example. Okay, determine the exponential relationship, which is this, that best fits the data of this table, where x is the number of years since 1921, and y is the population of British Columbia. And just so you know, this is a population question. In terms of exponential problems that you'll be seeing, you will always come across either population problems like with bacteria or deer or some sort of animal, or you'll come across radioactive decay problems. Those are the two types of common problems you'll always be coming across for exponential mathematical problems. So this is a population problem, and I went onto Desmos, and here's Desmos, and I made a table, and from that table, I popped this equation in. And again, you have to use the tilde. You cannot use an equal sign to get your best fit line. So this is the best fit line. And once you get that, then you have all this wonderful data. You have your A and B, and which fits into this equation. So with this data, I'll go back here. With this data here, this is Desmos. I was able to get this equation right here. Once you have the equation, and just so you know, population and growth problems, if you ever see a one in front, for population, mostly for population problems, you can break the equation down like this. If you notice, there's a one in front here and 0 point something. So basically, I'm just breaking this number down into 1 plus 0.02781. And most you will see a lot of problems that have this sort of similar form. So therefore, you can say that when the value of x is 0, when x is 0, it basically can't it turns this whole entire thing into 1. And 1 times anything is itself. So it becomes basically the value of the initial value when x equals 0 is 0.5250 million 52 million in 2001. This is when the population started right here. And the growth factor is about 0.027. And let's take a look at, yeah, 0.27. And you can tell right away that's the growth factor because it's right over here, this number here. And this is the reason why I like to separate the 1 away from this. Okay, so next problem. Estimate the population of British Columbia in 1985. Again, another population problem, and I like to separate the equation, take the 1 out, put 1 plus and this here. Yeah, and so if you need to find x, to use x, you subtract the number of years, the initial date, minus the date that you're looking for. So, well, the date, let's look at, so the date you're looking for is 1985. 1985 is 19, oh, well, here's 1981. I think it's supposed to be 1980. Oh, we're supposed to ask for 19. So 1985 minus the initial date, which is 1921. This is the initial date. And you'll notice that there are 64 years. Oh, sorry, I'm not using my mouse tool for this. About 64 years um, between those dates. So x will be 64. And using the equation we have, you drop in the 64 into the equation, and then you just find out what y is. So the population is about 2.9 in 1985. Now, why is this sort of important? This is sort of important because you're going to get a bunch of data, right? And you notice that you want to find something that's not in the data. Like, if you look here, there is no 1985. 1985 is somewhere in between here. So how can you possibly find what the population is? Well, if you can get an equation from this data, then you can make a guess. You can make a forecast. I believe that's the word, forecast, as to what the population is there, a prediction. So with the formula, when you have the formula, now you have access. You can figure out the population at any time, at any date. All you have to do is drop the number of years, where the x is, and then you'll find the population of that for that situation. Okay, I hope that made sense. Yeah, and that's about it.